All right, so we've talked about points, directions, and hexagonal, and now let's move on to planes. So crystallographic planes describe a plane like you know from math class, but again with the context of a unit cell. So we again kind of constrain it to this generic unit cell that you have, right? So this yellow shaded in region is the plane within the unit cell. So it's basically showing you the orientation of a plane within this crystal structure in relationship to the three axes, x, y, and z, or a1, a2, a z, and then again in terms of the links. So just like we've done with the other crystallographic features, I want to show you a procedure for how we can determine the Miller indices. In this case, again, the indices just refer to the numbers that we describe a direction or plane. Here, we call them the Miller indices for a plane because it's based on the scientist who came up with the strategy. So that's the only difference. If you just say indices of a plane, that's also correct. You don't have to say Miller indices. I just want to give you that terminology so that you know that when we're talking about Miller indices, we're talking about planes. So our procedure to determine a plane like the one is described here is 5 steps. So step 1, if the plane passes through the origin, we're going to have to move. It says more here, but it should be move. So we can't have our origin, or sorry, we can't have our plane going through the origin like you see here. So you'll either have to move the plane or move the origin. And so we'll talk more about that concept. And then what we're going to do is instead of doing projections like we did with a direction, we're going to look at intercepts of a plane with the axes. So we look at the axes x, y, z in this case, and we look at the intercepts of the plane with those axes. Then this is where the indice part comes in. To get a Miller indice for a plane, we actually use the reciprocals. So we take the reciprocal of those values that we just, the intercepts, and we take the reciprocals of it. So from there, though, it's very much the same. We adjust. We want to have the smallest integer possible. And then we enclose in parentheses this time. And if you're wondering why we're changing it from directions, it's because of that. We want to be able to tell the difference between a plane and a direction just by looking at it. So if you see parentheses like you see here, that is a plane. And then, as always, we're not going to use commas. All right, so let's work through this this example that I have, this plane that's shown in this unit cell. So that first step, if you remember it, is to move the origin if the plane passes through the origin. So again, like I said, you could do the sketch, basically put that plane somewhere else. But the easiest solution is to, instead of doing that, is to just pick a new origin. And so here, as you start out, you might just want to kind of trial and error, pick out a new origin, because you can pick out any of the corners. That's the easy way to do this. And obviously you don't want the plane going through. So I can't move the origin right here because the plane still intersects this origin. So at first, it might seem like a trial and error way, but as you do more of these, you'll understand kind of where's the best place to pick an origin. So for me, I'm going to put it over here. So this is the new origin, and I call that O prime just so you can tell the difference. I'm not having to redraw or anything. All I have to do is place my origin here. And then sometimes it's helpful to redraw the axis system like I have here. So I'm redrawing the coordinate system with x prime, y prime, and z prime starting here. All right, so we do that, and basically you want to try to just pick the most ideal location, and I'll show you what that means as we go through the next steps. All right, so I've got my origin, I've got my axis system. Now I'm going to read off the intercepts of the plane with axes. So these are my axes, and I want to basically identify where it intercepts each of the axes. And so just like I did with directions, I actually make this little table that you've seen before. Here I'm calling it x prime, y prime, and z prime because that's my axis system. So I want to make sure that you're aware that we're doing it based off of this one. And so when we first look at this, what we do is we'll first look at the x. I always like to go x, y, z, but you can go whatever direction you want. But if we look at the x prime axes here, and then if you extend it back and even look at the negative x prime axis down here, what you see is that you never see the plane intersect with that line. And so this brings up our first sort of complication with this, is that there is no intercept of the x prime axis with the plane. And again, that's any way you draw this, that's what you should find. And so when it never crosses a specific axis, that basically means it's parallel to that, and it intercepts, and we call that at infinity. So it's basically infinitely far away when it intercepts. Is basically just a way of saying it doesn't. So I'm going to put infinity and then a. That's the amount of the unit cell. On the second one, let's see where it intercepts the y prime. So you see here, the way it's drawn, it doesn't intercept the positive y prime, but it does intercept the negative. See, if you extend it this direction, that's the negative y prime, and it's back here at the origin, right? So that's 1 unit away, and it's 1 unit of b. So it's minus 1b because it's in the negative direction. So it intercepts right here. And lastly, this is our z prime axis, and you see that we do have an intercept right here. And this, as drawn, is half. So it's going to be 1/2 the c direction. So those are my intercepts with this new axis point. And if you're wondering why we couldn't have used the previous origin, again, because it intercepts the origin. So if you're looking at intercepts, that should be 0, 0, 0. And that just doesn't make sense. That doesn't tell you anything about a plane. So that's why we can't have it go through the origin and the coordinate system of interest. All right, so these are our intercepts. So now we're going to take the reciprocals, and this is where the infinity comes in here. So because we have an infinite or doesn't cross an axis, when we take the reciprocal of this, 1 over infinity, we're going to basically define that as 0. And then if we take 1 over everything else, we get -1 for so the same for y, but if we flip this, we get 2. So those are our intercepts, or sorry, these are our reciprocals of the intercepts. And from here, we adjust if we need to, but here 0, 1, and 2, those are the smallest integers we could have without fractions, and so that's not necessary in this step. And then the last one is we take those indices now and we put them inside of the parentheses with no commas, and again, the same way that the negative worked with a bar over it for directions is how we do it here. So that's kind of the procedure you're going to use for doing determining planes, the indices of planes in our system here.